Takaaki Kajita is the Special University Professor at the University of Tokyo and also the Director of the Institute for Cosmic Ray Research there. His famous research on the discovery of neutrino oscillations at the Kamiokande and Super Kamiokande detectors led to his sharing the Nobel Prize in Physics in 2015. It is fun for me to let you know that while Professor Kajita was thanking people after his Nobel Prize announcement, he also thanked the neutrinos themselves for their role in the prize. So we too can thank the neutrinos for right now for his lecture. Please join me in welcoming Professor Kajita.
Thank you. Thank you very much. Okay. Well, thank you very much for the introduction and also for the invitation. Well, today I want to talk about neutrino oscillations. And well, in fact, this is what I'm going to talk today. So, well, basically, I'm going to talk about the oscillation studies in the past half a year century, maybe 50 years. So, before the discovery, there was some interesting data on solar neutrinos and atmospheric neutrinos. Therefore, I'm going to talk about these early data. Then I'm going to talk about the discovery of neutrino oscillations by atmospheric neutrinos and the solar neutrino observations. Then I want to talk about the discovery of the third oscillation channel. And well, at this point, well, we almost understand the basic structure of the neutrino oscillations, but well, we still have some more agenda items for the future neutrino experiments. Therefore, I'll briefly describe these future measurements and I'll summarize. Okay, early days. Well, the photo at the center shows the home-stake solar neutrino experiment. And this experiment began more than 50 years ago. And this experiment successfully observed solar neutrinos for the first time. However, the observed event rate was only about 1/3 of the model prediction. And well, and this was about 50 years ago. And this is the well-known solar neutrino problem. And well, people worry about the, say, difficulty of the experiment. Therefore, people thought that we need an independent measurement. And therefore, following the initial observation by the home-stake experiment, several experiments observed solar neutrinos. And this is the summary of the observations in the 80s and 90s. So gallium experiments observed basically PP solar neutrinos, and the event rate was about 50 to 60% of the model prediction. And in the high energy part, around say 5 to 15 MeV, Kamiokande experiment and Super K experiment observed the solar neutrino flux. But again, the observed event rate was about 45 to 50%. So these solar neutrino experiments in the 80s and 90s confirmed the deficit of solar neutrinos. But at that time, we didn't know what was the cause of the deficit. Another story was in the atmospheric neutrinos. As you may know, cosmic ray particles enter into the atmosphere, and these cosmic ray particles interact with the air nucleus and produces pions. Then these pions decay to muons, then to electrons. And during this decay chain, 2 muon neutrinos and 1 electron neutrino are produced. And well, in fact, through the studies of atmospheric neutrinos, we come to the conclusion of neutrino oscillations. But for coming to this conclusion, there were two important key features. One is we understood the nu mu over nu e flux ratio quite well. And the ratio is controlled by the decay chain. Therefore, we thought that we understood this ratio. In addition, we understood the up-down flux ratio quite well. And in fact, this ratio is predicted to be essentially 1 above a few GeV energy range, where the geomagnetic field effects can be completely neglected. Then I want to talk about the early history about the atmospheric neutrino experiments. Well, in fact, proton decay experiments in the 80s observed many atmospheric neutrino events. And because atmospheric neutrino was the most serious background to the proton decay searches, it was necessary to understand atmospheric neutrino interactions. And during these studies, a significant deficit of atmospheric muon neutrino events was observed unexpectedly. And this is the early data from the 2 water-Cherenkov experiments. One was the Kamiokande experiment, another one was the IMB experiments. And both of them observed a significant deficit of muon neutrino events relative to the electron neutrino events. And here, mu over E ratio of the data are compared with the mu over E ratio of the Monte Carlo prediction. So quite a significant deficit of muon neutrinos. But at that time, again, we had no clear idea what was the cause of the deficit. Now, I want to move on to the discovery of neutrino oscillations. And the first one is the atmospheric neutrinos. And the most important experiment that contributed to the discovery was the Super Kamiokande experiment. It is a 50 kiloton water Cherenkov detector with a diameter of about 40 meters, and height is also about 40 meters, and which is about, the fiducial volume is about 20 times larger than the fiducial volume of the Kamiokande experiment. And the Super Kamiokande project was approved in 1991, and the construction began in the spring of 91. And in the year 1995, Super Kamiokande collaboration was trying to construct the detector itself in the Super Kamiokande tank. And these photos shows the construction of the Super Kamiokande detector. The left one shows the sidewall construction. So people were working at the bottom of the tank, and the wall of the detector was constructed. The right one shows the construction of the bottom PMT plane. So, well, the Super Kamiokande collaboration worked quite hard in the year 1995, and we were essentially ready in January 1996, and we started filling pure water into the Super Kamiokande tank. And the experiment began on April 1st, 1996, as we promised to the Japanese government. And well, from the beginning of the experiment, we had 2 targets. that two targets. And one was the atmospheric neutrino study, another one was the solar neutrino study. And this view graph shows the typical events we analyzed in Super Kamiokande. So in the energy range around 1 GeV, we have many contained single ring event. Okay, this is a typical single ring muon event, and this is a typical single ring electron event. Both of them are typically 1 GeV energy range. And if the energy of the neutrino is a bit higher, say 10 GeV, although neutrino interactions could occur inside the fiduciary volume of the detector, but the muon is typically high energy. Therefore, these muons penetrate through the inner detector, and therefore the event pattern is like this. So you can see the signal not only in the inner detector, but also in the outer detector, because the muon is exiting. In addition, in the energy range of about, say, 100 GeV to maybe 1000 GeV, we observe these kind of events. These are the neutrino interactions occurring below the Super Kamiokande detector. Then a muon produced by the interaction come from the bottom of the detector and pass through the inner detector and exit the detector. This kind of upward going muon is observed. So from the beginning of the Super Kamiokande experiment, we decided to use all these events for the analysis of atmospheric neutrinos. And in fact, I think Super Kamiokande collaboration worked quite hard in order to get the important result. And in fact, we thought that maybe atmospheric neutrino deficit observed in Kamiokande and IMB could be due to neutrino oscillations. Therefore, we wanted to clarify whether the deficit was due to neutrino oscillations or from the other reasons. And for this, we thought that way. Well, since neutrinos are produced everywhere in the atmosphere of the Earth, therefore some of them are produced just above us, maybe 10, 20 kilometers above us, but these neutrinos come to the detector only after traveling 10, 20 kilometers. Therefore, these neutrinos may not have enough time to oscillate. However, the neutrinos produced in the other side of the Earth, they have to travel long distances, typically 10,000 kilometers. Therefore, they may have enough time to oscillate. So, therefore, we naturally expect a significant difference in the upward going and downward going neutrino flux if the oscillation parameter was right. So we wanted to observe this effect, but well, actually I want to say we wanted to observe this kind of effect even in this Kamiokande experiment. However, well, we worked hard in Kamiokande, but we found that the Kamiokande 3,000-ton detector was too small to observe this kind of effect. So we definitely needed Super Kamiokande. Anyway, we worked hard, and after 2 years of the data taking, we were able to announce the evidence for neutrino oscillations. And this is one of the presentation slides at the Neutrino Conference in 1998. I don't want to go into detail, but well, let me explain this graph here I show you the Zinsang distribution. One means downgoing neutrinos, -1 means upward-going neutrinos. And these boxes show the prediction without neutrino oscillations, and these crosses show the data. And you can see upward-going muon neutrinos, number of these events are only about 1/2 of the predicted number. So with this, we thought that we had a very strong evidence for neutrino oscillations. In addition, as I said, we had another data sample, upward-going muons, and we also analyzed these data, and we checked if all these data are consistently explained by neutrino oscillations. And this is the result. So if we carry out two-flavor new mu new tau oscillations, the allowed regions largely overlap. Therefore, at that time, Super Kamiokande concluded that the observed Zinsang dependent deficit and the other supporting data gave evidence for neutrino oscillations. Okay, well, since then, there were a lot of experiments that carried out new mu new tau oscillation studies. This is the list of the experiments that studied new mu new tau oscillations. There are several atmospheric neutrino experiments, and there are several accelerator-based long baseline experiments. And these experiments studied neutrino oscillations. And I just want to tell you how much improvement we had in the understanding of neutrino oscillations based on the accelerator-based long baseline experiments. This was the K2K data. And well, at that time, compared with the no oscillation prediction that is blue, the data showed some deficit around 0.6 GeV. And this was the indication of the oscillation. Then the next one is minus. So they experiment a clear deficit of mu neutrino events around 2 GeV. Then here is T2K. So compared with the prediction, they tune the beam so that the oscillation maximum occurs at the peak of the flux. Therefore, they observed a really significant deficit of muon neutrinos. And this is the most updated NOVA result. And well, at that point, they had no interest in showing the no oscillation plot. They just want to compare the probably full mixing prediction and the data. So during the last 20 years, we had such a great improvement in the understanding of new mu new tau oscillations. And well, honestly speaking, all these data show only mu neutrino deficit. Therefore, on the other hand, we wanted to observe the appearance of tau neutrinos. And for this, the OPERA experiment was designed and carried out. And it is an immersion-based experiment, and they observed the appearance of new tau events by the direct observation of the production of tau and decay to other particles. They had observed five tau neutrino interaction candidates, and the expected background is small. Therefore, they have already a 5 sigma evidence. In addition, Super Kamiokande tried to get some information on the tau neutrino appearance. Unfortunately, in case of Super Kamiokande, it is not possible to get an event-by-event evidence for tau neutrino interactions. Therefore, in Super Kamiokande, we carried out statistical analysis. We select so-called tau-like events, then produce a Zinsang distribution. Then we only expect upward-going taus. Therefore, statistically, we estimate the appearance of tau, and at this point, the statistical significance is 4.6 sigma. Okay, now I want to move on to the next one, that is the solar neutrino oscillations. Well, the initial idea of the confirmation of solar neutrino oscillation came from Herb Chen in 1985. In that paper, he pointed out that the total neutrino flux and the electron neutrino flux should be separately determined. And for this purpose, he proposed a large heavy water Cherenkov detector. In a heavy water, we should expect a charged current interaction and also a neutral current interaction. Therefore, we should clearly observe the neutrino oscillation effect. And then, about 15 years later, the snow detector was constructed. It is a 1 kiloton heavy water detector, and it was located very deep in underground. It was 2 kilometers from the surface, and actually this 2 kilometer depth was necessary in order to reduce the sporation by cosmic ray muons. And this is these are the photos of the construction of the snow detector. And well, in fact, the pieces were transported to the snow site through the elevator of 2 kilometer length, but the size was limited. Available size for the transportation was limited. Therefore, well, according to them, 1 million pieces were transported down to the snow site and constructed at the site. And the experiment, well, filling the pure water and heavy water began in April 1999. And well, the technical challenge for the snow experiment was to detect neutrons. Obviously, neutrons does not emit Cherenkov photons. Therefore, you need to have some tricks to observe neutrons. And they decided to carry out 3 different ways of measurement of neutral currents. One is the pure D2O phase. In this phase, the neutron produced by the neutral current interaction is absorbed by the deuteron, then 6 MeV gamma ray is emitted, and they detect this gamma ray. In the next phase, they put 2 tons of salt into the heavy water, and then the neutrons are captured by the chlorine-35, and in that case, a total of 86 MeV gamma rays are emitted. And therefore, they detect these gamma rays, and in the final phase, they put helium-3 proportional counters, and neutrons are, of course, captured by this helium-3 counter. So they carried out these 3 measurements. And this is the result from the second phase. They had the measurement of the charged current cross-section, and also they had the measurement of the neutral current rate, and also in addition, they had the elastic scattering measurement. And here, supercameo can also contribute to this plot. And you can see 3 or maybe 4 different measurements intersect at a point. And you can see clearly the flux suggested is flux of mu plus mu tau is not there, not 0. Therefore, this is the evidence for non-zero mu plus mu tau flux. And therefore, we can interpret this result as evidence for neutrino oscillations. And this is the summary of the snow measurements in the 3 phase. And here's the measurement of the neutral current. And in all these measurements, the the results and the expected rate are just consistent. On the other hand, the charge current interaction measurement was always about 30% of the prediction. So from this data, Snow concluded that there is evidence for neutrino oscillations. However, well, people worried a little bit that the measurement by Snow was just a flavor change. So people wanted to really confirm neutrino oscillations. And for this, there was a Kamran experiment in Kamioka. And this experiment measured the anti-neutrino flux from the nuclear power stations around the Kamran. These power stations were, say, 150 to 200 kilometers away from Kamran. And through the measurement of the anti-neutrino spectrum, they plotted the event rate as a function of L over E. Then clearly, Kamran observed this kind of sinusoidal behavior of the disappearance. This is really neutrino oscillations. So people were convinced that electron neutrinos do oscillate. And finally, I want to mention more recent measurement by Borexino. Well, the measurement by Snow was here. But, well, there was a prediction according to the MSW mechanism that the oscillation probability as a function of neutrino energy should be like this. Here is the vacuum oscillation dominated region, and here is the matter oscillation dominated region. And these are the measurement of the Borexino experiment. And with this, basically, we are confident that the data are just consistent with the MSW prediction. Okay, now I have to speed up a little bit. Well, after these two discoveries, the people's interest in the neutrino community was the discovery of the third oscillation channel. And the third oscillation channels were studied by these experiments. One was the accelerator-based long baseline neutrino oscillation experiments. Another one was the reactor-based short baseline neutrino oscillation experiments. And, well, surprisingly, these experiments gave an evidence for the finite theta 1-3 in a very short time in year 2011 to 2012. The data at that time is shown here. So accelerator-based new appearance experiments observed the appearance of electron neutrinos, and the reactor-based experiments observed the deficit of anti-electron neutrinos. So from these measurements, we can say that the basic structure for three-flavor neutrino oscillation has been understood. And this is the numbers. Maybe for this conference, maybe I can simply skip. And, well, I said that basic structure for the three-flavor oscillation has been understood. However, in my opinion, neutrino physics are not over yet. And, well, this is maybe still a partial list of the agenda for the future neutrino measurements. Well, I said we basically understood the structure of the neutrino oscillations. However, we are not sure yet which is the heaviest neutrino state. That means nu3 mass state is heaviest or lightest. We do not know. So we'd like to confirm if, for example, if this is the right picture. We do not know if the oscillation probability for neutrinos and antineutrinos are identical. Well, this is a very important issue. Maybe the CP violation in the neutrino sector could be related to the baryon asymmetry of the universe. And related to this, we'd like to know if neutrinos are Majorana particles, and we'd like to know the absolute neutrino mass. Neutrino oscillation experiments can only tell us the neutrino mass difference. And finally, we'd like to know if there is a structure beyond the three-flavor framework. Okay, let me summarize. Proton decay experiments in the 80s observed many contained atmospheric neutrino events and discovered the atmospheric neutrino deficit. And subsequently, in 1998, Super Kamiokande discovered neutrino oscillations. And solar neutrino experiments began in the 60s. Various solar neutrino experiments before the year 2000 observed the deficit of solar neutrinos. Then the SNOW experiment discovered solar neutrino oscillations by the measurements of charged current and neutral current reactions of solar neutrinos. And since then, various experiments have studied neutrino oscillations. And at this moment, I can say that the basic structure for three-flavor neutrino oscillations has been understood. And finally, the discovery of non-zero neutrino masses opened a window to study physics beyond the standard model. Okay, that's all. Thank you very much.
So again, we have a chance for a question or two, Professor Kajita, and we would take the microphone to you. Anything?
You mentioned a few times that the measurements has deficit compared with the theoretical prediction. Do you have that much confidence in the theoretical prediction since all these years?
Well, okay, I think you're talking about the solar neutrino deficit. Yes, that is a very good question. In fact, people are really not convinced about the quoted error of the theoretical calculation. Therefore, in a sense, people wanted to get theory-independent measurement showing that the deficit is due to neutrino oscillations. And the SNOW experiment was the one that carried out this measurement.
So it's a very naive question from a non-neutrino physicist, but another big question, of course, is the nature of the neutrinos masses, whether it's Majorana or not. And there's all these neutrino double beta decay experiments going on to investigate that. It always surprises me that there's no link between what we see in the mixing matrix and what we might see in the Majorana mixing parameters associated with it. Either experimentally or theoretically, is there really nothing you can learn from long baseline or oscillation experiments about the nature of the neutrino masses other than the delta M squared?
You mean about the Majorana nature?
Is there no impact if you introduce the Majorana mass and mixing matrix alongside the PMNS matrix? Is there no preferred values for the parameters or anything like this that give you a clue about that nature of the neutrino mass?
Well, if the question is either Majorana or Dirac mass, then in my opinion, in my understanding, we have to rely on a special experiment telling us the Majorana nature. And as far as I know, the only experiment that can tell us about this nature is the neutrino-less double beta decay. And unfortunately, at this moment, there's no evidence for the neutrino-less double beta decay.
I just wanted to make a theoretical comment. Neutrino oscillation only changes the... Just a theoretical comment. Neutrino oscillation only tells you that the electron number for a given family is broken. It's not a good symmetry. Then when you put Majorana masses, you break the total electron number. Then you need to find that tell you that the total electron number is broken to make the point. It doesn't matter which process, but you should go in that way. That's why neutrino oscillation never can tell you about more than that.
May I? Yes, hello. I have a question for you. What about Hyper Kamiokande? Can you tell us the status of that program?
Okay, thank you very much for asking this question. Yes. Well, I can tell you the status. Well, we are quite serious about the realization of Hyper Kamiokande. And in fact, last year, there was a government review about the roadmap of our funding agency, MEXT. And Hyper Kamiokande was selected as one of the big projects, big scientific projects by MEXT. MEXT selected only 7 big projects among all science and technology fields. And as far as I understand, Hyper Kamiokande was actually in the higher ranking of among 7. And therefore, essentially, government should decide the Hyper Kamiokande to move on to the real project. However, there is a problem. Now, Japanese government is getting poorer and poorer. And therefore, the official approval is not received yet. Well, we do not have the official approval yet. But we are working hard to get the approval from the government. So I really hope that we can hear good news in the near future.
I do have a minute to ask something that was connected and brought up this morning. Professor Kajita, you recall we were talking at lunch about the fact that we had this online interaction with the public in Reddit AMA this morning. And in it, there was a question about is there some possible practical usage or some practical implications of what we are learning about the Standard Model? Well, if you forgive me, I'm not going to be connecting to the grocery store, but it occurred to me that looking at your pictures, when you were looking at neutrinos going through the Earth, is there the possibility of learning something about the Earth's core through this, especially maybe sensitive to the oscillations and so forth?
Oh, yes, yes. In fact, if we have, say, next generation neutrino experiments such as Hyper Kamiokande, and if we operate this detector about 50 years, we should be able to tell the interior of the core, core of the Earth, if they are made of, say, heavy element or light element. That kind of thing we can tell.
May we thank Professor Kajita again, please.
Thank you.